talking about slow sand and rapid sand. The difference between rapid sand and slow sand is the flow rate at which you can treat water. Rapid sand can treat water at a faster rate, meaning you can treat more water. Another difference is the pore size. Slow sand pore size is 0.2, rapid sand is 0.45 to 0.55. And a graded layer is present in rapid sand, and you have only one type of layer in fine sand. Graded layer usually a smaller pore size at the top, fine sand, and a coarse sand at the bottom layer. We started talking about the disadvantage of having a fine sand layer at the top. With the fine sand layer at the top section of the filter can get clogged faster than the bottom coarse sand layer. So to have efficient filtration, I mentioned about having a coarse layer at the top and a fine layer at the bottom. So in rapid sand, fine sand at the top clogs faster than the bottom coarse layer. So we need a system, need a setup with coarse layer, which is larger grains or bigger grains. Now grains are the particles that are in the filter bed, or you have the filter, what you fill the filter with is called the grains. So we need a setup with a coarse layer, usually larger grains at top and fine grains at the bottom. So with this setup, what happens is smaller particles will pass through the larger grains but will trap the bigger particles at the top. Now as the water flows with the smaller particles towards the bottom of the filter, the fine grains will trap the smaller particles and you get clean water out of it. So for this, I'm going to turn on the projector for a second. Okay. So what we see here is the dual media on the top. Two types of media. You have the coal and the sand. Now what is happening here? Dual media filter. Typically coal at the top and sand at the bottom. Now coal has lower specific gravity compared to sand. So you can have bigger size coal at the top and relatively smaller size sand at the bottom. This setup will allow to remove bigger size particle at the top and smaller size particles at the bottom. That way we can take advantage of the entire depth of the filters. So 1, 2, 3, the effective pore size can be optimized based on the need. So in this setup, coal will be held at the top as a loose layer and the fine sand is at the bottom. Now this figure right here is the pore size distribution. What you have is depth and pore size. So this is the top, this is the bottom. At the top you have smaller size coal right here. So you have the lower pore size. As you go deeper, the coal size is increasing, so the pore size increases, meaning you have bigger openings in between the coal particle that will allow larger particles present in water to be trapped. Now at this point, which is about midpoint of the filter, you have the fine sand. Now fine sand, they are more compactly packed, meaning there is lesser space in between them. So your pore size decreases. Now as you go down, you have bigger size sand particle, so the pore size increases. So this is the idea of two types of media, two dual media, where you have coal that has a bigger pore size at the top and sand, smaller pore size at the bottom. Now this allows us to take advantage of the entire filter or all the depth of the filter. A modified version of dual media filter is multimedia filter or mixed media filter. In this case, mixed media filter. Now generally you have three types of media. So you have, well, let me talk about this figure for a second. So we have the coal, sand. This is the initial setup. So you start out the filter with a coal and sand layer. Now as you pump water through it, the material inside or the granules inside the filter will rearrange. That's why you see that the fine sand layer here, as you start using the filter, the fine sand will move along and get trapped in the bigger coal layer. So that will to some extent reduce the pore size. So these sand particles take up the pore spaces. So if you compare these two figures, this is the pore size distribution for the same type of figure. This is at the startup before you start pumping any water. This is during operation. During operation, you have some of the sand particle, fine sand particle, getting mixed with the coal layer, so the effective pore size decreases. So this part is due to the mix of sand and flow layer. The pore size here is relatively narrow compared to this one. You have a wider pore size, the biggest here, smallest here, and somewhat in between. Once you start operating, you have a smaller range compared to the fresh filter media. So this is the multimedia. In generally you have three media. In this case you have coal, sand and garnet. The typical distribution is 60%, 30% and 10%. The specific gravity for each type. So coal has a lowest specific gravity of 1.6, 2.6 for sand and 4.2 for garnet. Meaning this is the heaviest material, the one with highest density. This one has the lowest density. Like we saw before, the intermixing is allowed. Intermixing will happen. Now pore size. So this is specific gravity. Now pore size in millimeters. For coal it's about 1.0. For garnet it is 0.15. For the sand, in between, or it's 0.15 to 1.0 for sand. In between, less than 1 but greater than 0.15. So with this setup, we have a bigger size particle with bigger pore space in between them at the top, and the smaller size particle, smallest pore space, and the heaviest at the bottom. So this figure shows the particle distribution for mixed media. You have coal right here, garnet, sand. At the top, it's mostly coal, relatively less sand and garnet. At the very bottom, garnet is this is the particle distribution percentage. So highest percentage of garnet is at the bottom. Now sand, somewhere in the middle you have the most sand. So it is arranged in a way that top coal, mid sand layer, bottom garnet layer. Now this is pore size. This is depth, top, bottom. So if you look at this one, you have the biggest pore size at the top, because you have the coal at the top, which is bigger in size, and it has lower specific gravity, so it can stay on the top. The smallest pore size is at the bottom, which is due to garnet, which has the heaviest or highest specific gravity. So higher density, it will stay at the bottom. Since it's a smaller particle, the pore space in between them is small. So with this arrangement, bigger particles are removed at the top in coal layer. Relatively smaller particles in water are removed in the sand layer. And the most smallest particle or finest particle are removed in the bottom garnet layer. So what we've seen is, we've seen 4 types of filters. One is slow sand, one type of media, same pore size, usually fine sand. So it's mainly, the mechanism is surface process, where particles are trapped in the top surface, slowly allow a biological mat to form on top of it, and more particles are trapped in the biological layer. And that slow sand process does not take advantage of entire depth. So it forms at the top, you clean the top, and then again allow water to pass through. Again, there is a buildup at the top, you remove it. So you can only treat limited amount of water with that. So then people came up with a rapid sand technology, where you have 2 types of sand layer, a fine sand at the top and a coarse sand at the bottom. Coarse sand will have bigger size pore spaces, the space in between the sand particles in the filter. Fine sand will have the smallest. So rapid sand allowed more water to treat in a shorter time. So slow sand about 3 to 8 meter cube per meter square per day. Rapid sand you can treat up to 120 meter cube per meter square per day. So it's a faster process. Again, the idea is fine sand at the top, coarse sand at the bottom. The problem with rapid sand is the fine sand layer traps all the smaller particle as well as the bigger particle. So oftentimes you don't end up using the entire depth of the sand. You won't effectively use the coarse sand layer at the top. So a better system is having a coarse or bigger type particles or bigger granules at the top of a filter and finer granules at the bottom of the filter. This setup will allow bigger particles to be trapped at the top, smaller particles to be trapped at the bottom. With sand, and this arrangement is not possible. Arrangement meaning having a bigger size sand at the top and a fine sand at the bottom is not possible because of specific gravity. You can arrange it, but as soon as you pass water through it, the fine sand will go to the top, coarse sand will get to the bottom. So people looked at different materials, and one effective material was coal. Coal has a relatively low specific gravity compared to sand. So you can arrange bigger size coal at the top with bigger spaces in between them and the fine sand at the bottom. This way you trap or you filter the bigger particles at the top, filter the smaller particles in the fine sand layer and get the clean water flow through it. So it was efficient. 2 types of media, dual media. You can increase the rate from anywhere between 300 to 600 meter cube per meter square per day. So much faster process, more efficient. And even more efficient was a mixed media layer where you have coal, sand and garnet. Garnet has the highest specific gravity. So we looked at the pore size distribution. Again, pore size meaning the space in between the filter media or what you have inside the filter to filter the water. So the material inside the filter in a mixed media is coal at the top, sand at the middle and garnet at the bottom. And this was even more faster than dual media. So it turned out very effective. I want to solve an example problem. So design monomedium, one type of medium, rapid sand, filter. So we're going to design a rapid sand filter with one type of medium. Well, obviously rapid sand, it's made of sand, it's just that 2 different sizes. Fine sand at the top, coarse sand at the bottom. Now the flow rate to treat, design a rapid sand filter to treat 18,400 meter cube per day. Estimate number of filters and dimensions. So we are going to design a rapid sand filter for this flow rate and calculate the number of filters and the dimensions of the filter. Now, solution. Flow rate, if it's less than 8,000 meter cube per day, two filters minimum. If flow rate is greater than 8,000 meter cube per day, you need 4 filters minimum. There is also a formula to calculate number of filters. Number of filters n equal to 0.0195 times Q raised to the power half. Now Q is the flow rate in meter cube per day. So you calculate the number of filters needed by 2 methods, and whichever gives the higher one, we'll use that one. So using this formula, n equal to 0.0195 times flow rate is 18,400 meter cube per day raised to the power half, this is equal to 2.65. So based on the formula, you need 2.65 filters. In other words, you need 3 filters. But we also have a condition where if the flow rate is above 8,000 meter cube per day, you need a minimum of 4 filters. Therefore, use 4 filters. Again, based on the formula, we calculated we need 2.65 filters. We can't build 2.65, so it has to be 3. But we also have a condition where if the flow rate is above 8,000 meter cube per day, you need minimum of 4 filters. You calculate by both. Look for if it is greater than 8,000 meter cube or not, and then use this formula. Calculate the number of filters needed by both. Whichever is higher, you take it. In this case, it's greater than 8,000 meter cube per day flow rate, so 4 filters is minimum. This is greater than 2.65, so I'm going to use 4 filters in this design. So, number of filters equal to 4. Now we need to calculate the dimensions. So area of the filter bed A equal to Q, which is the flow rate, divided by N, number of filters, times Q. So capital Q is maximum flow rate, lowercase q is filtration rate. So this is in meter cube per day, meter square. This is in meter cube per day. And N is number of filters. Okay, these are the formulas, and in general what we need is area of filter bed. Ranges from 25 to 100 meter square. Depth of filter bed is 4 to 8 meters. Well, there's two things. Filter box and then depth of filter bed equal to 2 to 3 meters. So this is the area, length times width, that is straightforward. Now depth of filter box, depth of filter bed. Now filter box is where you have your filter inside. Filter bed is where the actual filtration is happening. If you're using a rapid sand monomedium, the sand is in the bed and there are other things you need in a filter. We'll look at an example filter figure that will show you what the box is, what the filter bed is. So typically, filter bed is where your filtration is happening. So in rapid sand filter, sand is in the bed, you pump water through it, and the particles in water are removed in the filter bed. Filter box is where you house your filter bed. There are other things needed in a box, so it's usually bigger than or deeper than the filter bed. I'm going to take a break now. We'll come back and design the dimensions.